Okay, so let us get back to check why this is the unbiased estimate. Okay, so why we want to have a sample mean? Because the goal is mu. So if we can have the expectation of the estimate and reach the goal, right? If we have this, and such an estimate is called the unbiased estimate. Well, here we need to check why. Right? And we know if we have this, it should be this. Right? And for these, they are mu. Right? From from 1 to n. So we have n mu. So finally we have a mu. So this one meet the requirement. Expectation of the estimate allow us to reach the goal. So of course, this is an unbiased estimate. This one, no problem. And for this, the same. The estimate allow us to have the sample, not sample, the expectation equal to the goal. So that's why we want to have n minus 1 instead of n. Okay, so for this reason, we have these. However, for this one, how to reach the result? At this moment, maybe this one left you at this moment. Okay, so you need to check. The same, you can apply the property of expectation, and so that you can check it is true or not. However, at this moment, maybe for saving time, I allow you to check for yourself. All right. Okay, so if we have a sample mean using expectation that says get mean, check the first moment so we can know it is an unbiased or not. And also we can have a variance for the sample mean. And finally, we have the results here. Variance. It's the original variance over sample size. If we have the results here, it says larger sample size or bigger sample size, then we should have the concentrated results. That says dispersion is small. All right, so concentrated result says the sample mean can approximate mu properly, right? All right, so this is the way to have the interpretation for the sample mean. However, if we want to know the variance of sample mean, usually we have the approximation. Because real variance not really easy to be known, but sample variance achievable. So we can replace real variance sigma square by its sample variance. As for sample size, this one is known, so of course no problem. So that's why if we want to have the estimation, we can use sample variance over the sample size. And later I can show you these. Why? But talking about correlation, because of IID, so we don't have a correlation. We don't have the correlation. Sometimes, or maybe usually, it is not true for the cases. So that's why it's too strong to apply the assumption IID. IID, they ignore any possible correlation. So this one, it is not the proper assumption. Why not proper assumption? Sometimes we should have the way to capture the correlation. And this one asks you to skip to capture the correlation. So the assumption is too strong. Okay. All right, so right now, now check this. Why? Look at this. So n, we have n squared. And this is summation. Sorry, not this. Summation already. And previously, they are IID. So IID means independent. So we have the summation. Okay, so for all of the variables, they are the same. So it should be n squared. So finally, it's this one. That's it. All right, so this is a way to explain why a variance of a sample mean equal to sigma squared over n. Okay, so I let you know this. Well, I think maybe you guys have a question about the previous one. I asked you to exercise to check because that one it takes you a long time, and likewise take me a long time to explain. So I think it is worth doing that in the actual time slot, but not the classes. So that's why I ask you to check for yourself. All right, after classes. So I encourage you to do. If you fail to do, I think still okay, but at least you need to check why. All right, so up to now, IID. So using IID to serve as the assumption, is it okay? It says it has been, it says, we know the output data are almost always correlated. So correlated, it says, not equal to 0. However, if we have a too strong assumption, for example, IID, then you cannot capture the correlation. If we want to capture correlation, how to do? Maybe we can have a real situation, but the real situation perhaps not very easy to handle. If we want to have an easy way to handle, we can employ the previous assumption, covariant stationary stochastic process. If you apply covariant stationary stochastic process, then you can have the way to have the estimation. First of all, think about this. How about sample mean? It says still an unbiased estimate because their property is irrelevant to IID or covariant stationary, or even no specific discretion. We still can that equality holds. So that's why sample mean is still an unbiased estimate. However, if we choose the same assumption. For the sample variance, right now, no longer an unbiased estimate because we cannot have the property to get the summation of the individual variance. So that's why we cannot use it. And if we cannot use it, then it is not an unbiased estimate for sample variance. Okay, so why? You can look at these. The same, this one, left to you to check. It can be shown for sample variance, and previously you are asked to practice this for yourself. If you follow the current discussion here, IID, then we have a zero correlation, zero, then this one zero. So of course for the previous one, mean of a sample variance equal to the goal, and then it should be the unbiased estimate. However, right now, if we have the covariance stationary stochastic process with the assumption, this one normal zero, normal zero. So can we reach the goal? No, we cannot reach the goal. So that's why we cannot have the unbiased estimate if we have a sample variance under the assumption of covariance stationary stochastic process, right? All right. You can treat this result as a given result if you don't want to prove it. However, if you want to prove it, then you need to know why. Okay. If you know why, and then you can understand the results. Well, using the previous result, it says if we have the positive rho sub j, that says the positive correlation. And then it says the expectation should be lower than sigma square. If lower than sigma square, so not real, not approach sigma square, so not okay. And likewise, you can check variance of these. The same. You can check this problem and this problem that you have the similar result. Why I call similar result? Because you have the similar form. So that's why I let you know the similar result. And if so, how to have the covariance? How to have the correlation? You can have a lag J covariance using this way. This time, we don't care about the modified sample size. Here, how many sample size? It should be n minus j because finally there are a gap j. You cannot have the pair to have the cross term. So that's why you need to minus j. And minus j becomes the real sample size. Should we minus one further? No, because this time we don't want to pursue the unbiased estimate because it is impossible to reach an unbiased estimate. So we don't care about that. All right. And actually, if we want to have IID, still want to have IID, how to do? It says we can have a warm up. And also it says you can have the good simulation output data. And so that you can use the group to have the averaging value. Average value, okay, by averaging the data so that you have the average value. For all the average value, it follows IID possibly. So that says if indeed you want to have the observation valid for IID, you still can do so. How to do? You can have the good simulation output data. And based on the group simulation of data, you can have the IID assumptions. And that's it. So that's why sometimes you need to use a good simulation of data, and so that you can apply the assumption IID. So it says this one, generally speaking, not valid, but if you want to make it, you can use a way to make it so that you still can based on IID to have the measure. Okay, so I think this one, it's a repeated discussion. Previously, we already know. Okay, that's all. So this is explanation of mean variance and correlations. Well, up to now, any question? If yes, let me know. Let me check any question from some of you. Well, maybe no question indeed. So let me continue. Next topic, we will talk about confidence interval and hypothesis test for the mean. All right, so how to do? All right, so we may have the two ways to show the confidence interval. And this is a theory for the confidence interval. So I think if you can understand this one, and then you can apply the current results. But the current result asks you to have some measure first. First of all, we use normal. Normal distribution. Well, if we want to have the good approximation, n is sufficiently large. This one okay for us. And it says this one perhaps not exact, but it is an approximate this percent. 100 multiply 1 minus alpha percent confidence interval. And this is the formula. Okay, so this is a further discussion. First of all, think about this. We assume IID again. All right, not confined stationary. And if we can have the random variable, sample mean minus its goal, and over the variance of the sample size, a sample mean. Here, this is a variable, for example, y, and this is a variance y. You see? So variance y minus its mean, and over the square root of variance y. So this is a way to define random variable. And you can have the CDF for this random variable. And in the following, we have a theorem to that you have some idea. Okay, of course, n should be large enough. And phi z, it is the CDF of the standard normal. So central limit theorem says if we allow n approach infinity, then we will have the standard normal. What that means, standard normal, it's zero mean and unit variance. Okay, so 0 means mu equal to 0, variance equal to 1. This category is called the standard normal. All right, so this is a central limit theorem. So this one says if n large enough, this one approximate normal, standard normal. And right now, the variable defined here use the goal of sigma square, right? And mu, why we don't care about mu? Because mu will be disappear in the following expression. So of course we care about the value of real standard, real sigma square. If we want to have the proper sigma square, how to do? This one can be replaced by the sample variance. Okay, so this one. We can have a sample mean first. Plus or minus this variable, multiply these. Okay, so this is first one using normal. Using normal, what that means? It says we can use this z and minus this z. And this is the this is a confidence. So what confidence means? You have a probability here. Okay, given 1 minus alpha, multiply 1000 to reach the percentage, right? But right now, if you don't care about the way to express in percentage, you simply use the normal value 1 minus alpha. Okay, so this is a probability 1 minus alpha. If we have a normal, then we should have the symmetric figure. Symmetric figure, so 1 minus alpha. So for the remaining, actually we have alpha. So the probability here should be alpha over 2. The same here because of a symmetry. If we have that one, so what is the accumulative probability? Of course, it should be this. 1 minus alpha over 2. So that's why we have this one. And for normal, we have the symmetric value minus 1, then that's done. All right, so this is a way to determine the two endpoints. Once we determine the two endpoints, we can have the expression here by using normal. Okay, so how to reach this? If we have the interpretation here, we have this result. What minus 0 z with the probability with sub 1 minus alpha over 2, and the previous one plus. You guys should understand this. Let me erase some of the description here. Right? If we have this, multiply both sides. and this one reverse it so that it's mu minus and still meet these. Right? And plus one, plus mu. Plus x bar, not mu. So finally, we should have these. So the concept here actually follow the interpretation of a normal symmetric one so that we have a positive one and minus one and put them together if we are given the constraint with the confidence of 100 multiplied 1 minus alpha. Then we have this way to construct the normal random variable to have the confidence interval. And that is finally the form here. About this, any question? And no, another similar one, we do not base on the normal distribution. In fact, we base on T distribution. So T confidence interval. If a T almost the same because the shape perhaps different, but follow a similar form, but we have the similar form here. T, and we have two parameters, n minus 1. N minus 1, I think you understand. It is the degree of freedom. And the probability is 1 minus alpha over 2, the same as the previous one. Okay, so it says if we have the observation follow the normal random variable, it says about this this random variable, it has the exact T distribution. Because of exact T distribution, you can follow the concept of normal. We should have the similar form, but we need to check the threshold from Z to T. And here Z to T follow the degree of freedom n minus 1 and probability 1 minus alpha over 2. Well, even this is the exact result, but in practice, the distribution of x sub I will rarely be normal. So that says the approximate equation is given only. Okay, that's it. So up to now, any question? If no question right now, we just follow the previous expression. Perhaps expression 2 to have the constant interval. First of all, I think you guys check, is it true? And check sample variance, is it true? Okay, so this one, I think if you have the tool, perhaps the calculator, you can use your calculator to verify this one true. If it is true, then we just follow the formula. And here we have a T. Because we have a 10 here. So n minus 1 is 9. And 1 minus probability here, this is alpha. Sorry, this is 1 minus alpha. So we have this. If we have these, we should follow this flow. Right? So that's why we have the probability here. If we have this, and then what to do? I can have a table for you. And you can look up the table in the task book. Well, right now, not okay to open this file. Okay, so maybe this time I cannot open the file, but let me check where we can have the file. Okay, so at this moment, maybe I cannot find another one so that we can open it. Well, something wrong. So this time, maybe I cannot let you look up. You can check the task book. Let me check the page number. Wait a moment. Let me try to take a photo. So you guys let me have a time to find the table from the task book, and then I try to have that photo for you. Okay, I try to take a picture for you. Maybe not so
clear, but at least you can refer to this.
I think right now you guys use the photo. Okay, use the photo. And previously we have 9 and value 0.95. And right now we can look up T using the first column by finding 9. And not first column, ninth row, we have a 9. Actually, the first column it's new. New, we find the corresponding value 9. And with 9, map it to another one, 0.95. And what is the target value you've seen? It should be 1.833, right? 1.833, that says this. Through table lookup, we have this. Previously, I just tried to have the table because failed to open my file. I need to make sure, but I try to find the table and take a photo for that. And right now you have that. You see, we have these. Let me use the photo to show you some of the results. So how to do? We use this. 9. Here it's n-1 is 9. And the probability map to this. This one. Okay, probability and n-1. So map it to this value. Okay, so we can use the table so that you can look up T. With the T, and then you can have the confidence interval. That's it. All right, so this is the result. I think you guys understand me how to apply the table. As for the number to have the table, let me check the page number. $722. Okay, so you can refer to this page of the table, and also you can retry the other values. All right, so this one, I think, if you have the table, you can check the page number on 722, and so that you have the table. All right, so I think this one okay for you, right? If you have the given value, You see, if we have the given value, we have the given value. Then this one you can calculate, and this one through table lookup. So you have the given value. With all the given value, then you can have the confidence interval, right? And furthermore, notice this, how to construct confidence interval. How many observations for the given value? 10. For example, previously someone asked me, number of customers, perhaps you can set it to 1,000. Once 1,000, then what to do? You can alter random seed. Okay, alter the random seed. So even you have the same string number. Okay, even you have the same string numbers, if you can alter random seed, then you can have a different output. All right, this is really important. Think about this. If you do not alter the random seed, but run the source codes 10 times, what happens? You will have 10 the same values. Okay. However, if you can alter the random seed, this time you don't have the same value, but you can have different 10 values. For example, here, if you have the different 10 values like this, and then you can have the confidence interval by using the calculation. All right, and that's all. So is it okay? All right, so this is the way to have the confidence interval. Look at this. Second expression. And this is the first expression. For the first expression, where to find these? I tell you, look up the table again. If you want to find z, that's really easy. All you need to do, you need to have this. Previously, you just have 0.95 without the degree of freedom. Well, no need to have a degree of freedom, this one. I get back to that file again. This one. Using the column, using the row here, the final one to infinity. To infinity right now, it's this one. So z here, for the previous example, z, it should be 1.645. So it says, if I will use this example, T and Z, right? Which one larger? T larger. T larger means the confidence interval is a larger interval, but Z is a shorter or smaller interval. Why? Because normal. This is T. So of course, if we want to have the same probability, T will provide you a larger interval because the probability for the two sides will be thicker than, T distribution has a thicker tail than the normal. Of course, for the center side, T distribution has a less probability there because it tries to spread the probability to the two sides. So that's why looking up the table, you should have a larger T for the confidence interval, but a smaller Z for the confidence interval. And which one we prefer? Of course, T, right? Because T, that does have the confidence interval. And also T will meet normally, and that's all. All right, so this is the confidence interval. Think about this. We can follow the formula to have the calculation. And sometimes if you look up, for example, Excel provides you the confidence interval as well. However, before you adopt the value from Excel, you need to check, is it true? The formula correct? All right. So if you think that's okay for you, you can apply the results in Excel. But normally, if you don't want to rely on the formula in Excel, you can input the current formula here, and so that you can have the exact calculation. I mean, the formula is correct, so the calculation is correct. But normally, if we use the T distribution or the other distribution, it's an approximate confidence interval. However, the formula is given, so we think it's an exact calculation. All right, that's it. This is the confidence interval. And next time, this time maybe we cannot finish all. So next time we will reach the discussion for the hypothesis test. Okay, so later we will have some other discussion. Okay, so it's all, and right now it's time's up. So I just want to ask you any question about the today's discussion. If no, this time, next Monday, it is a firm due date. So you should understand all and try to finish the programming assignment. All right. I won't send an email, but at least you keep in mind, I extend the due date to the next Monday. This is the first thing. And the second thing, I think, right now, I think you can review. And I made that you have the reference exercise from chapter 1 to chapter 3. I don't that you have any reference exercise. This time, no need to hand in, but I will provide you a solution. You can treat, you can write your answer down and try to check the solution after you finish the reference exercise. Of course, since chapter 4, we have the reference exercise, so you can do it. I think if you can do it, you will understand more for the content of chapter 4 and also chapter 6 and 8. We will do the same thing. Okay, so later if I think time's ready, I mean, if it is okay, I will release the reference exercise to you guys, and so that you can know how to practice. All right, so up to now, any question? If no, that's all, and see you next week. Bye-bye.